Hello, I'm David Nichols, and I'll be describing work done in collaboration with Bradley Kavanagh, Gianfranco Bertone, and Daniele Gaggero on the dynamics of dark matter in IMRI and EMRI systems and its effect on the gravitational waves emitted from these systems. Let me first remind you that there's strong evidence for the presence of cold dark matter on the largest scales of the universe, such as in the fluctuations of the CMB and large-scale structure, and in individual galactic rotation curves. However, there aren't as many observations on smaller scales below that of galaxies, but there are a number of interesting ideas of possible dark matter substructures that can form. One intriguing one is due to Gondolo and Silk, who imagined a scenario where a small seed black hole is formed within a larger dark matter halo, and then over time, this black hole accretes mass slowly so that it grows, and so that the gravitational potential of this black hole changes and becomes larger. As a result, the dark matter surrounding the black hole tends to get compressed into an object they called a dark matter spike. And this dark matter spike generally was assumed to be a spherically symmetric object and follow just a single power law in terms of radius, denoted by gamma spike. In this talk, I'll consider spikes that are of parsec scale, where the normalization of this density is between hundreds and thousands of solar mass per cubic parsec, and the spike is in a narrow range between 3 halves and 5 halves. Similarly, I'll consider the spike to form around an intermediate mass black hole, so an object between 1,000 and 100,000 solar masses. And I'll also consider the possibility that this system of black hole and dark matter spike captures a second compact object, M2, which I'll assume to be of a neutron star mass. For this talk, I'll consider the object M2 to be on circular orbits, and I'll describe these orbits and the dynamics of the dark matter just by Newtonian physics. However, I'll also include two leading order dissipative effects. One, which is a simply vacuum effect due to the emission of gravitational waves from this IMRI system, and a second, which is another Newtonian effect known as dynamical friction, where dark matter particles that are moving more slowly than the orbital velocity of M2 tend to scatter off of M2 and form a wake behind it. This wake forms a kind of drag, and this drag also decreases the orbital separation R2 between the neutron star and black hole, and thus forms a second source of dissipation in the system. Now, this scenario had been considered before by Ada and collaborators in 2014, and they found, not surprisingly, that this additional source of dissipation, dynamical friction, speeds up the inspiral. So from a given orbital separation, the system undergoes fewer gravitational wave cycles before merging. And this dynamical friction effect produces what we would describe as a negative post-Newtonian order of effect, which is a relatively high negative order. It goes like the power law of the spike, minus 11 halves. And what they found was that this phase difference can be quite large. So this is a typical example that they found for an intermediate mass black hole of 1,000 solar masses and a second compact object of 1 solar mass for a few different power laws of the spike. In particular, for the case gamma equals 7/3, the solid line, for a system that would merge within 5 years, the presence of dark matter would cause a significant dephasing. So it would undergo around 1 million fewer cycles, whereas the system starting from this orbital separation would tend to just undergo a few million cycles. So this causes a very large dephasing effect. And as a result of this, one can ask how well one can measure the parameters of such a system if one has appropriate templates. And Ada performed this exercise for Lisa using a Fisher matrix analysis. And they found, not surprisingly, that the chirp mass can be measured exceedingly well because the system undergoes so many cycles, but also because of the very large dephasing effect. For the specific case of gamma equals 7/3, the spike can be measured to a few parts in 100,000, which would be a very remarkable measurement and would allow one to learn a great deal about the distribution of dark matter around the intermediate mass black hole. However, there's one important caveat about their result, which is that they assumed that the distribution of dark matter is static throughout the entire inspiral, the compact object. So as this mass m2 goes from some large radius to some smaller radius, it loses energy, and part of this energy that it loses is dissipated through dynamical friction, and this energy dissipated through dynamical friction goes into increasing the average kinetic energy of the dark matter particles. And this is what I'm denoting by delta E dF. But there's only so much available energy that can be dissipated before the dark matter particles scatter and become unbound from the system. That's given by the binding energy of the system, it's delta U dm. So when delta U dm is of the order delta E dF, then that would mean that as the object inspirals, it would significantly disrupt the spike, and one should therefore not assume the spike is static throughout the inspiral. So we computed this ratio, and we found that for a wide range of binaries for different mass ratios, in fact, the dissipated energy was much larger than the binding energy of the spike. So everywhere where there are red or orange colors, this ratio is greater than 1, whereas for blue colors, it tends to be smaller than 1. So for systems with mass ratio 10 to the minus 3, much of the parameter space for different power laws and different normalizations of the density has this property that one should not consider the spike to be static throughout the inspiral. Okay, so then we would like to have some way to evolve the distribution of dark matter. This is what I'll now describe. So to do this, we started from the phase space distribution of dark matter, which we assumed to be spherically symmetric, so we could write this function f just as a function of the energy per unit mass of the dark matter particles. The relationship between the phase space density and the usual density is just given by integrating over all velocities. Then we developed a prescription for how to evolve the phase space density on timescales longer than the orbital time, and under the assumption that on these longer timescales, the halo maintains spherical symmetry. So our prescription is, in essence, just detailed balance. So the phase space density changes due to the fact that some particles of energy E scatter with M2 and are moved to higher energies or lower energies E plus delta E, which takes away particles from the phase space distribution, hence the minus sign. And then there's a second term in which particles with energy E plus delta E undergo a similar scattering process with M2 to an energy E. And this then increases the phase space density. And ultimately, we have to integrate overall possible scattering energies to get the net change in the distribution function. So as a first test of our procedure, we considered the case where the compact object just sits at a fixed orbital radius, and we were interested in what happens to the density of the particles, specifically those moving with speeds less than the local orbital speed of the particle, because those are the ones that contribute to the dynamical friction effect. What's shown is that the initial power law slope shown here over time gets depleted in the vicinity of the orbital radius of the particle, and some amount of the particles gets sent to a larger radii, or in other words, greater energies. And this process tends to continue to deplete as long as the particle or neutron star in this case, stays fixed at an orbit. So we have a prescription for how to evolve the dark matter distribution, and now we'd like to solve the coupled system equations, which is namely the fact that there is some energy dissipated, so the neutron star will sink towards the black hole, and then the phase space distribution will continue to evolve in this process. So this leads to an interesting set of equations, which are shown schematically here, which are an integral partial differential equation coupled to an ordinary differential equation involving the binary separation. And these functions here are just schematic functions to show the dependence of the orbital radius on both the orbital radius and the density. Then the evolution of the density depends on both the orbital separation of the binary distribution function and certain integrals of the distribution function with respect to energy. Okay, so we were able to implement this system. Although they're complicated looking equations, there's a straightforward algorithm with which to do this. Standard techniques for solving PDEs work. And this is what we find. So the red result, this curve, shows the result of eta for an analogous system of a neutron star spiraling into a black hole, where the system has a mass ratio of 10 to the minus 3. So whereas eta was finding the dephasing for a static halo would be of order 10 to the 6 cycles during the last 5 years before merger, we're finding when we take into account the dynamics of the dark matter distribution, the depletion of the dark matter in the vicinity of the particles significantly decreases the number of cycles of dephasing to more on the order of 10 to the 4, so 10,000. So it still is a large number, but it's several orders of magnitude less than what eta et al. Predicted. Though because it's so large, there still are good prospects for being able to measure the presence of dark matter around black holes. So next, I'd like to show what happens to the dark matter itself. What I'm showing in blue is the density for all particles, and in red, those whose velocity is less than the circular velocity at that radius. We're interested in the final 5 years of merger, but we start at a larger radius because, as I'll now show, in this first few years, with these initial conditions, there's a significant depletion of the dark matter particles. But nevertheless, even though there is this depletion, the total density of particles is not changed so much. Then I'll greatly speed up the time scale for the evolution so that it involves a few hundred years to get to the initial conditions that we would like to study. And as you can see, as the system inspirals to about 5 years before merger, a large number of the particles get pushed to larger energies and fill in this gap that was near the orbital radius. Now, during the final 5 years, you see there still is a significant depletion of the number of particles. But during these last 5 years, gravitational wave emission takes over, and the particle inspirals so quickly that there's actually no longer significant depletion of the dark matter density as you move to the smallest radii. Okay, so as my time is nearly up, let me wrap up. So what we have found is that if a dark matter spike forms around an IMRI system, one should take into account the dynamics of the dark matter, because not doing so can lead to significant overestimates of the effect of the dark matter on the evolution of the IMRI. Nevertheless, although including dynamics means that the size of the effect is much smaller than not including dynamics, it still is large enough that the prospects for detection are promising. However, there's a lot left to be done in terms of studying these kinds of systems, both in terms of the astrophysics of understanding the formation scenarios, the rates of these mergers, to improving some of the waveform modeling beyond the Newtonian approximation using circular orbits, finally thinking about issues related to the detection prospects and how well one might be able to estimate the parameters of these systems using the LISA detector, which we're currently thinking about this work in development. So I invite you finally to look at the paper, this preprint on the archive, which describes this in more detail if you found any of the work here interesting. Thank you for your attention.